Next up, we're going to talk about one of the biggest appeals of computational multiphysics, which is this idea of conjugate fluxes. So this is going to appear pretty obvious to a number of you and pretty confusing to a different number of you. So we'll see where you land here. The idea is that we want to get away from empirical boundary conditions. So what I mean by that is we've all probably encountered at this point convective heat transport, where we're talking about a surface that is convecting into the atmosphere, for example, and we've linearized that with some kind of generalized parameter. We want to get away from that and use our computational tools in order to get a better mechanistic understanding of that physics that's going on in the adjoining domain. So what I mean by all this is that we're going to couple different types of physics in different domains and have the fields talking to each other. Instead of using, well, it is still a boundary condition because it is through different domains, but you'll see what I mean with an example. So this example is from this week's tutorial, which is on heat exchanger. And the setup here is that we have a solid block, which is indicated by this highlighted region. And then through the block, we have some channels of a fluid that's being passed one way and another way. Now in the solid, all we have is heat conduction through the solid. In the liquid, we have both conduction in the liquid, which is small, compared to the advective current. So the advection is the fluid that's flowing and pulling away that heat as it's going. So if you've ever mixed up a pot of water, for example, you've done convective heat transport. Now, the magic is that we're actually solving the same temperature field for inside the solid and inside the liquid. And because that's fixed all along the boundary between those two, it is requiring the heat flux from the solid to be pulled away into the liquid. In doing so, we get away from empirical approximations, where otherwise we would have to have an approximation for the convective heat loss around that inner surface. Instead, what we're doing it now is we're actually solving that physics simultaneously, even though the fluid physics is only happening inside these channels, not inside the solid. This particular example, we're going to use an empirical velocity profile. In general, actually next week, we're going to get away from that, and we're actually going to solve Navier-Stokes simultaneously only within these channels, and therefore even get a better approximation of the real physics behind this. This is a reflection of something called the continuity condition. Basically, what it's saying is that we are not solving two different problems that are coupled. We are actually solving a single problem. And in finding a unified solution, we gain a mechanistic understanding of what's happening. In this particular case, because of the structure and because of the modes that are built into COMSOL here, we don't, this coupling between the domains is built in. Since we're doing the same field inside the solid and the liquid, you'll notice that there isn't a boundary condition on the surface of these channel walls. It's because it's automatically assumed that the temperature on one side is actually shared with the temperature on the other side. In general, this won't be the case. What you're going to have instead is some other variable, some other field, T2 for example, that only exists in one domain, and then you couple those two through your Dirichlet conditions, right? This is why last week or last lecture I went through the different types of conditions. Now, do remember in that warning, when you couple something with Dirichlet, you're implicitly assuming something about the fluxes. And the fluxes have to be consistent with that Dirichlet coupling. But this is actually the benefit. This is where the conjugate heat transport, in this case, is coming away to pull away that temperature. Okay. I should note that this particular physics happens because the nodes are actually shared between the two domains. For more exotic finite element types, I'm not sure we're going to get to those in this particular course, but there are certain conditions where that won't be the case. For example, if you ever encounter something called discontinuous elements, that in general won't be the case unless you explicitly put that in. Okay? I should note that this is actually something called two-way coupling. I'll show you a nice example. Oops. Well, guess I won't show you an example. Let me recompute that and then I'll show you an example. Thinking. Okay, so this is going to be our result. And I'm just going to add on arrow surface here to show you. And I think I needed 1,000 arrows. Oops. And I'm going to show you the velocity profile here. Here we go. So these arrows are the velocities along these channels, and it's carrying away the heat. You can see that the heat is being pulled out of the adjoining solid. Okay, this is called two-way coupling because the temperature profile inside the fluid is being coupled to the temperature inside the solid in a way that's consistent in that the information is flowing both ways. It can be one-way coupling. There are more exotic ways that we can put that in. Sometimes that would be useful. It would decouple the problem, which makes it a bit simpler computationally in order to solve it. Generally, we're going to have to talk about one-way coupling when we get there.